Hi everyone, welcome to Edu-Malanga if you're joining us for the first time. And if you're joining us for the manyth time, welcome back. We're still working through the Matric Mathematics syllabus of South Africa and we're covering the third unit of the year. The third unit of the year looks at exponential and logarithmic functions. Today we will do example 2 and example 3. And these will be the last two examples we do on this unit. If you're joining us for the first time and watching this video, I hope you have a good understanding of exponential laws and functions. If you don't, we do have 3 previous videos where we introduce exponential functions and exponential laws, and we do an example on these topics. So go back to the other videos on this channel. They will be under the playlist covering Unit 3. So let's get started with today's examples. We're going to do example 2 and example 3. In example 2, we're given this exponential equation and we're asked to solve for x. The equation is 16 times 4 to the power of x plus 2, that whole expression times 1 over 4, and it should be equal to 4 times 1 over 64 to the power of x. So we have to solve for x in this equation. When we work with exponential equations, we need to put everything under the same base. For example, a to the power of x equal to a to the power of b. When it's all under the same base, then we're going to be able to say x is equal to b. So let's look at these exponents. We've got 16 and we've got 4, and then we've got 1 over 4 and 4 and 1 over 64. So it looks to me like if we choose that 4 will be our base, because it's currently the smallest number that we're seeing, we will be able to have the same base on both sides. So let's start working with both expressions to make 4 the base. We'll start on this side. I'm going to rewrite the equation on the next page, but I'm going to change 1 over 4 using the inverse power law. So the equation will then be 16 times, keep the brackets, 4 to the power of x plus 2, close, times 4 to the power of minus 1. And then I'm also going to change this side as well using the same law. So it'll be equal to 4 times 64 to the power of minus x. Now that we have removed all the division, let's turn 16 and 64 into 4 to the power of something. 16 is equal to 4 to the power of 2. So here we can say 4 squared times, open brackets, 4 to the power of x plus 2, close, times 4 to the power of negative 1 should equal to 4 times, again, 4 to the power of 3 is equal to 64. So on the side we're going to have 4 to the power of 3. We're going to have brackets times negative x. So now we've turned everything into the same base. We simply have to simplify on both sides. On this side we have multiplication happening, and when you multiply an exponential exponent with the same base, what you do is add the exponents. So let me simplify this side then. We're going to have 4 to the power of 2 plus x plus 2 minus 1 should equal to, and this is this expression simplified. I've simply kept the same base and added all the exponents, because that's what the laws of exponents say you do when you multiply exponential terms with the same base. On this side, we have the 4 as it is, but the power law says we must multiply these exponents. So on this side, we're going to have 4 times 4 to the power minus 3x. So let's simplify all these numbers. We have 4, we can say 2 plus 2, that's equal to 4, minus 1, so that's 3 plus x on this side. Here we have to bring everything under the same base. So we're going to have 4 to the power of 1 minus 3x. So now we have the same base on our equation on both sides. That means that the exponents are equal then. So 3 plus x is equal to 1 minus 3x. Let's group like terms together. We're going to take the negative 3 to this side of the equation. It'll become a positive 3, and we're going to take this positive 3 to this side of the equation, and it'll become a negative 3. So we're going to have 3x plus x should equal to 1 minus 3. 3x plus x is equal to 4x. And this side is equal to 1 minus 3 is negative 2. So therefore, we're solving for x. X is equal to negative 2 over 4, which is equal to minus 1 over 2 when you simplify it. And this is how you solve exponential equations. Let's move on now and look at example 3. In example 3, we're given the function f of x is equal to 3 to the power of x, and we're told to 1. Draw the graph of this function. Then we're asked to identify the y-intercept of the function. Question 3 asks us to identify the horizontal asymptote of this function. We're then asked to plot the graph of g of x now, which is 3 to the power of x plus 3. And we're asked to determine how does addition of this 3, affect the behavior of the graph. It's a lot to do. We'll do it step by step. Let's get started. First, we'll draw the graph of f of x is equal to 3 to the power of x, as we've been asked to do in question 1. Let's rewrite the function here. F of x is equal to 3 to the power of x. We're going to have the values of the domain, x values here, and then we're going to have the values of the range over here. We'll start from negative 3, negative 2, negative 1, 0, 1, 2, and 3. At this point, I suggest you pause the video and you use your calculator to find out the values of the range. You're first going to substitute in negative 3 in the place of x. You're going to do it for negative 2, and you're going to keep doing this until you get to the last value, which is 3. I've already done this beforehand, so I'm just going to fill in the values. When x is negative 3, y is 1 over 27. I'm going to write this down as a decimal as well, because the decimals help me to estimate better when I'm drawing the graph. So 1 over 27 can be written down as 0.037. Now let's solve for when x is negative 2. When x is negative 2, y is equal to 1 over 9. In decimals, this is equal to 0.111. And when x is negative 1, y is equal to 1 over 3. That's equal to 0.333. So these are the decimal numbers that will help us create the graph. When x is 0, y is equal to 1. When x is 1, y is equal to 3. When x is 2, y is equal to 9. And lastly, when x is 3, y is equal to 27. These are the values we're going to use to create the graph then. Let's draw the graph on this axis. We'll start with the 0 term. When x is 0, y is equal to 1. So let's get started. Plot it over here. Yes, and we'll move to the negatives. When x is negative 1, you have 0.333, so you have about a third on the y. X is negative 1, you have about a third on the y, which should be approximately here. When x is negative 2, you have 0.111, which is even smaller. Okay, that may be about even there. And when x is negative 3, you have 0.037, which is also much smaller. Round about there. Let's draw on the positive side. When x is 1, y is 3. And when x is 2, y is 9. We're not going to be able to plot this on our graph because the values end at about 13. But let's plot everything. When x is 1, y is 3. And when x is 2, y is 9. So now let me draw the graph. The graph of y is equal to 3 to the power of x looks like this. I'll write down y is equal to 3 to the power of x. So we've just solved the first question. Let's move on now and answer the second question. The second question asks us to identify the y-intercept of the function. You can simply come back to this table. The y-intercept happens when x is 0. Y-intercept is 1. So for question 2, the y-intercept is equal to 0, 1 for this function. The third question asks us to identify the horizontal asymptotes of the function. Let's come back again to the graph. It's the best way to see these things. We can see that our graph is moving closer and closer to the x-axis. We've only checked the numbers up to -3. Let's see, for example, if we say f of x is equal to 3 to the -6. What is the answer? Again, use your calculator to check this. In my calculation, I found that it's equal to 0.00137. So the numbers are getting smaller and closer to the x-axis, but they're still not touching it. So therefore, horizontal asymptote is equal to the x-axis. Let's now answer question 4. Question 4 asks us to plot the graph of g of x, which is equal to 3 to the power of x plus 3 now. Let me write down the function. G of x is equal to 3 to the power of x plus 3. And I'm going to choose my domain value to start from -5, -4, -3, -2, -1, 0, 1, 2. These are the domain values, which are the x values. And over here, we're going to write down the range values corresponding to each domain value. Again, I suggest you pause the video and use your calculator to solve for the values of the range. Guys, it's very important that you do the pausing, because if you learn to do these things alone, you'll be very comfortable to do it in your test and your exam as well. So please pause and use the calculator. I've already done this, so I'm going to just fill in the values. When x is -5, y is 1/9. And if we remember, 1/9 in decimals is 0.111. When x is -4, y is 1/3 in g of x, and this is 0.333. When x is -3, y is equal to 1. And when x is -2, y is 3. When it's -1, you have 9. For 0, you get 27. I'm going to stop right here because I know already anyway in my graph paper I won't be able to draw the rest because it stops at 13. I'll just start on the left on this graph. When x is -5, y is 0.111. On the graph we have -5 being really low, and then when it's -4 you have 0.333. It's -4, it goes to about 1/3. Okay, when x is -3, your y is 1, and when it's -2, your y is 3. Let's plot that. -3 goes to 1, and 2 goes to 3. The last value that we can plot is when x is -1, your y is 9. When x is -1, your y is 9. Okay, let's draw this graph. It's looking like this. And let's write down the equation as well. Y is equal to 3 to the power of x plus 3. The last question, question 5, asked us to describe how the addition of the 3 affects the behavior of the graph. So we have to look back at this graph, and what can we see? Originally, when you have y is equal to 3 to the power of x, the graph is here, and when you've added 3, the graph has undergone a translation. It's moved to the left, and by how much has it moved? Let's do a calculation. We'll use the points. For y is equal to 3 to the power of x, when your x is 2, your y is equal to 9. And for y is equal to 3 to the power of x plus 3, when x is equal to -1, your y is equal to 9. I've just realized I've called these graphs wrongly. Let me fix that now. This graph is g of x, so let's cancel y. And this graph is f of x, so let's cancel y as well. Sorry about that mistake. Let's continue and calculate by how much the graph has moved to the left. You have 9, so you have the same y value. You've gone from it being 2 to minus 1. To move from x is equal to 2 to x is equal to negative 1, you must move by 1, 2, 3. So you've added 3, and what you've done is you've moved the graph to the left by 3 units as well. So when they ask us, how does addition of the 3 affect the behavior of the graph? We can say that the graph moves 3 units left. This question is helping us revise the effect of any number when you add it to the exponent. So let me use the basic expression to explain this. If you have y is equal to a to the power of x, and then you change it into g is equal to a to the power of x plus n, when the value is plus n, the graph will move n units left, and when the value is minus n, the graph will move n units right. So if we had minus 3 in this graph, what would have happened is that it would have moved this side, and we would have seen a translation of the graph in this way if we had minus n. That is the effect of adding or subtracting any number from the power of your exponential function. I hope I've explained everything in these 2 examples clearly and you have understood. If you are confused by anything, please feel free to leave questions for me in the comments. I'll try my best to answer them. We've reached the end of these 2 examples. Thank you for joining us. Join us in the next video where we will introduce a new lesson, and the lesson that we will look at is going to be logarithms.